We're going today to talk about factor groups. These generalize the integers mod n. So what we had is we call for integers a and b and z. We had a congruent to b mod m, if and only if the difference is divisible by m. And so really this is a special case of A plus B inverse is an element of the cyclic subgroup generated by M. And in general, we talked about mod n, so that's a special case of congruence mod H, where H is a subgroup of G, where we'd say A is equivalent to B mod the subgroup if and only if A, B inverse is in H. This is a right equivalence using a right equivalence mod H. And so what Zn is, or in Zn, the congruence mod M is really congruence mod that cyclic subgroup in Z under this. So really what we were doing in the integers mod n is we were adding cosets. So let's see how we can create a coset, a group of cosets. And we'll call that a factor group. So that's going to be the topic of today's lecture. So what we can do is, given a group, G a group, A, B is not necessarily subgroups, but just subsets of G. We define what I call in the notes multiplication of complexes, A times B, just to be the product of every element of A and every element of B. So in particular, if we have two cosets, so if H is a subgroup of G, AH times BH is just going to be A times H, B, H prime, where H and H prime are elements of G. Sorry, elements of H. A, H, B, H prime. So basically A times anything in A times H, anything in AH times anything in BH. And clearly multiplication of complexes is associative. If you look at the product of A, B with C, so what is that? That's all A, B, C, where A is in A, B is in B, C is in C. But we have the associative law in the group. We can put that over, and that's A, again, A and A, B and B, C and C. And that's exactly A times the product of B and C. So again, when I say a multiplication of complexes, we're thinking a complex is simply a subset of a group. And the multiplication of complexes is just all elements in one subset times each element in the other subset. And it's a way of giving two sets. Think of this as a product. Here's two sets, A and B. Here's a product. Is a third subset of G. So we see that multiplication of complexes is associated. But the question is, if we take the product of two cosets, do we always get a coset? So let's look at an example. Let T be the group of matrices with, they all have 1 and -1 and 0 as entries. So T, matrix group of 8 matrices. And H is a cyclic subgroup generated by this particular matrix. Which just consists of the matrix itself, and I believe if we square it, we get the identity. And so if we take AH, so let's look at a little a to be that, little b to be that, AH would just contain A, and then the product of A times this element, which would be -1, 0, 0, -1. And BH would be this element, and then also that element times the identity, and that element times this, which would give us 0, -1, 1, 0. So these are your two cosets. So let's multiply them together with that definition. You'll see you won't get a coset. So what we have is AH, BH. That's just the product of all four together. So it would be this element times that element, and then that element times the second element of BH. Then we take second element of AH, this one. Something. So what's in AH? These should both be negative. Right? When I multiply by this, that would give us, this would give me a -1, this would also give us a -1. So then you take the second element of AH and multiply by both elements of BH. And so what would we get? This would give us a 0, -1, 1, 0. This would give us 0, 1, 1, 0. This product would give us 0, -1, -1, 0. And finally that product would give us 0, +1, -1, 0. And this is not a coset of H. Right? All the cosets of H have to have two elements. So we can see for a general subgroup, this is not going to work. The product of two cosets defined by multiplication of sets, what I call multiplication of complexes, is not in general going to give us a coset. So we wouldn't have a well-defined multiplication, right? If we want to have the cosets make the cosets in the group, we need the product of these two cosets to be a third coset, and that's not the case here. So let's see if we can see what is necessary and sufficient for a subgroup H to have the property that AH, BH would be a coset. As I said, we've talked about this in our last face-to-face meeting. We've gone through some of this as well in factor groups. But I'm going to continue to present it here on the video. So what do we need? Well, in general, we have, no matter what subgroup A, B, H is contained in AH, BH. That's what we really want. We really want equality. So we want, seems like if you're going to multiply two cosets, AH and BH, the way to do it would be to multiply the elements A and B and then find that coset. So we really like equality between the sets. We always have this containment, since if X is in A, B, H, that means X equals AB times some little h, where little h is an element of the subgroup. But we can rewrite that as X is equal to A, E, B, H, and that's an element of this complex because E is an element of the subgroup H. So we always have that containment. What about the other containment? So really what we want is what is what do we need for the reverse containment, which would give us an equality, which would give us equality of the two sets. So what we do certainly, if G is abelian, if X is in AH, BH, that really means there exists an H and an H prime in H with X equals AH, BH prime. But if it's abelian, we can write that as ABH prime, and that's an element of ABH. It's H times H prime. And remember, H is a subgroup now, so that product of two elements, H and H prime, is still an H. So certainly if it's abelian, we have that. But if you think about it, what do we really need? We really need that this should equal, we'd really like it to be A, B, or say H prime H. So really this is the condition we need. So what's going to happen? We need this for every B in G and H in H. Again, because this element so we need that there exists an H double prime in H that allows us to make this commutation. So if you think about what this really needs, this will be the case. if BH equals H double prime B, or in set notation that would be the left coset determined by B is the same as the right coset determined by B. In other words, we need H to be a normal subgroup. So if we have a normal subgroup with that condition, we'll be able to satisfy this equation, and therefore any x that's in AHBH will in fact be in ABH, and so we'll have equality of these two sets. Our claim, if H is a normal subgroup, then for all A, B, and G, AH times BH is just the same as ABH. So proof, we've essentially proved it. We already saw for any subgroup, it's always the case that ABH is contained in AHBH. Remember how we could just put an identity unit in there, so AEB times something in H would work. What about the other equation? We'll take x in AHBH, just like before. We have, there exists H prime, where just like we've already written it below that, x equals AHBH prime. But there exists an H double prime in H with BH prime equal to H double prime, well, let's say, actually what I need is HB is equal to BH prime, and again, that's since H is normal. And so then we have, that means x is in fact A, B, H double prime, H, which is in A, B, and H. Since x was an arbitrary element of AHBH, of the product of those two cosets, we have AHBH is contained in ABH. And so since we always, anytime without a normal subgroup, any subgroup gives us the other inclusion, we have these two sets are equal. So really this tells us that not for any subgroup, but for a normal subgroup, we can define the multiplication of these two cosets. They in fact will equal coset and they'll equal this coset. So theorem, let G be a group and N a normal subgroup of G. So define the set G, it's read G mod N. So this is just the collection of, well, I could say left cosets, I could say right cosets. The group's normal, so it's the same. So it's the collection of, I'll take left cosets, AN and G. Then Gn is a subgroup under AN times BN is just ABN. And how many elements are there? That's just what's called the index of N in G, using that symbol. Again, that's the number of distinct cosets. The group consists of cosets, so the number of elements in the group is just the number of distinct cosets you have. So the proof of this, we've already shown that these two things are equal, a set. So certainly this set is in fact going to be a coset. The product of these two sets. Is it well defined? So suppose AN equals A prime N and BN equals B prime N. We must check that the resultant product on the one hand, I can take this product. On the other hand, if this AN is equal to A prime N and BN is equal to B prime N, we'd have to take that product. So in other words, we have to show these two cosets are equal. So again, that's a well-defined issue. So what do we have if these two left cosets are equal, AN equals AN, we have A inverse times A prime is an element of N, and B inverse times B prime is an element of N. Now looking ahead, we want to show that the inverse of this times that is an element of N, or B inverse A inverse times this element is an N. Here we have these two equations. That's what it means for these two left cosets to be equivalent. And that's what it means for this equation, is what it means for those two left cosets to be equivalent. So let's go about showing this. So let's look at B inverse A prime, B prime. So this equals B inverse H B prime for some H in N, because A inverse A prime is in N. But this equals, this H we can commute with B, so we have B inverse B H prime, we'll say H prime, for some H prime in N, and that's since B is normal, so H is a normal subgroup, so B prime. So B prime N is equal to N B prime. So here we have an element of N times B prime. We can flip that and make it B prime times some other element of N. And the left-hand side of that equation hasn't changed. But what does this tell us? This tells us that this has to be an element of N, right? Since B inverse B prime is an element of N. And so that's an element of N. We're multiplying by H prime with an element of N. So N is a subgroup. Those two, the product of those two are in N. But what does that mean? So we have, this is really AB inverse times A prime B prime is an element of N. So that's exactly what it means for ABN to be A prime B prime N. So the multiplication is well defined. Okay, the rest of it should come fairly straightforward now. We have the associativity. We already proved that anytime we multiply subsets of a group, what I call complexes, that's associative. So we've already shown that the product of this set, think of this as an A, think of that as a B times C, is equal to that for all cosets AN, BN, CN in the factor group. So again, we've just seen the associativity of this multiplication of sets, we've already shown that works. So we've proven this previously. What about so that's the associativity. What about the identity? Well, for any coset in that group, if I multiply on the right by the identity, by definition that's that, and the property of the identity is just an. So the coset en is in fact the identity, because multiplication of it on the right. What about inverses? Well, if I multiply on the left by A inverse is a group element, so A inverse determines a coset. So that would be a coset determined by A times A inverse, or just En is the identity. And then if we have both a left identity and a left inverse, is enough to show we have a group. Way back in groups, we proved that earlier. I think I proved that if you have a right identity and every element has a right inverse, that's sufficient to have a group, and the same with the left. As I remarked in the lecture note, it's really no problem at all just to show that En is also a right inverse, a right identity, and A inverse N is going to be a left, is going to be a right inverse as well. But we don't have to. And so we note, I'll give that separate. And then the, as I said, the number of elements of this group, this is a group of cosets, so this is the number of distinct cosets. And so equals what we call the index. So that completes the proof. The group G over H, G mod N, is called a factor group or a quotient group. We just add a corollary or another theorem or just a proposition, we'll call this maybe. If G is abelian, then its factor group by any subgroup is abelian. I guess actually since it's abelian, I'd say for H a normal subgroup of G. But I'll just say H a subgroup of G. So what would the proof of that be? So first just let's note, since G is abelian, any H is not only a subgroup or N is a normal subgroup. Right, clearly, because a left coset is definitely going to be the same as a right coset if the multiplication is commutative. That's certainly necessary, though not, that's sufficient, though not necessary to have an abelian group. So there's no problem, so this is a group. Right, remember, looking at the cosets of any subgroup may not give us a group, but if the subgroup is normal, it does. And then clearly for any two cosets in the group, this product is AB, but now the group is abelian, so that's BA, and it's just equal to that product. And so now we see what Zn is really Z mod the cyclic subgroup generated by M for Z under addition. So the integers mod N, they really are a factor group. Factors of the cosets determined by multiples of M. Multiples of M is that's the same as the cyclic subgroup generated by M. So let's maybe calculate some examples. Let me just say UM in general is not a factor group. Right? I mean, really, if you think of cosets of Z under multiplication, multiplication Z isn't a group under multiplication. But the integers mod M are a first really example of a factor group. So let's look at some further factor groups. So I want to look at the group of 6 matrices G, and we have I, A, B, C, D, K. And look at the subgroup generated by B, which is just B squared is B, and B cubed is I. And this is normal. In G. We've seen that by a specific example, and also in the cosets we've actually proved that if a set has if there are only 2 distinct cosets, then in fact the left and the right cosets have to be the same. So this will happen because B has 3 elements, G has 6 elements, so there can only be 2 distinct cosets. So let's look at the Cayley table for this group. So what is this group? So it has two elements. The first coset is just the subgroup itself, I, B, D. And the second coset, we could look at the coset determined by, for instance, A. A times I is A. A times B is C. A times D is K. Again, if we want to give these a representative, we can say this is I, the coset determined by I, and the coset determined by A. So again, in the factor group, we sort of, a whole set collapses. We think of each coset of a collection of elements as a single element. And so what's the Cayley table? So we have this set, and then list the elements. So if I multiply each element in this, I times that, I get these three elements, B times that, I'd still get those three elements, D times those three elements, I'd still get those three elements. And then I times this would still give me these three elements. Similarly, this coset would now give me these three elements, and this coset times this coset, you get like A times A, that's A squared, that's I. A times C, that's, I think, B. And A times K, which would be D. So there's the Cayley table of that factor group. That factor group only has two elements, so there's really only one way you can have a two-element group, right? Just an element A, whose A squared is the identity, and then just the identity. So let's look at another Cayley table. Again, so T is going to be those matrices with zeros and ones. So I put them down in the notes. Again, there's an 8-element group. So it's the identity, something that looks like this, something that looks like this, something that looks like this, and then the negatives of these. So just to say board space, I'll put plus and minus in front of each, and those are my 8 matrices. And then we're going to want to look at the subgroup. We're going to look at Z of T, the center. So what's in the center? Well, certainly the identity commutes with every matrix, so it's going to commute with all those matrices. And the negative of the identity also commutes with all matrices, so it's going to commute with all those 8 matrices. So I claim that is in Z. Certainly those two elements commute with everything. But could there be more? I try to show that it's not. So how did I do this in the notes? I looked at this product. And I think that product was not the same as reversing the order. So that can't be in the center. Again, what is the center? The center is a set of all matrices that commute with every element of T. And so this matrix doesn't commute with that matrix, so this matrix. But that matrix doesn't commute with this matrix, so that other matrix is not in the center as well. Then I think if we put a negative in front of everything, those two matrices don't commute. Oh no, I think I covered that. I'm looking at the right one. Let me see. That's just a string mark. So those are not equal, so neither of those two in the center. Again, what I'm trying to show is that only those two elements are in the center. So since it's a small group, I'm trying to rule out. Nice thing is once you get a product of two things that don't commute, you can throw both of them out. So far these four are thrown out. I don't think we've looked at these two matrices. I think those two matrices actually they actually commute with each other, so we have to maybe look at some other examples. So if I take, for instance, this product here is not going to equal that product. So that tells us that that can't be in the center. And then finally, I think if we look at put a negative ones in front of it, that product is not equal to each other. So those two element matrices are not in the center as well. So these two do commute with every matrix, and the other six don't. So the center is just those two elements. So let's begin to look at the Cayley table now of this group. So what is the order of T mod the center? That's just the number of distinct cosets. which is just the order of t over the order of the center, which is 8 over 2, or 4. They may be saying, wait a second, Blau, how do we even know we have a group? Do we have a normal subgroup? Remember, certainly the center is normal, right? Every element in the center commutes with everything in G, so certainly A times something in the center can be written as something in the center times A. So let's look at the cosets. What are the cosets? So we have the identity coset. I'm just going to write, there's only one group going on here. So I'll put Z for the center instead of Z of T. So that's one element of our 4-element group. Let's get the remaining cosets. So we want to pick something that's not contained in those two. I'll pick -1, 0. Let's see. And so that, of course, gives me the representative. And then if I multiply it by the negative of the identity, it will give me that. So that's a second coset. So now we've got 4 elements. So we've got 2 cosets. We've got 2 more cosets left to go. I think I'll pick this coset, and it always contains the representative itself and the representative times the negative of the identity. That's our third coset, and finally, what's left is only 2 elements that we haven't picked. Let's look at, say, 0, 1, -1 Z, so that's contains the representative itself, and then the representative times the negative of the identity. So that's the only element in Z besides the identity. And we get that. And so we'd like to do the Cayley table. Let's start with, as I said, calculation. Let's look at, for instance, this coset times this coset. So we multiply these 2 representatives together. This will give us a -1, 0, 0, -1. We get that. Is that even, let's see, this should be -1 times 1, 0 here. So that coset is the same as what 2 elements are in here. It's going to be these 2 elements, so that's, we can rewrite as that. Okay, again, when we have the Cayley table, usually if you could pick different representatives, but usually we want to stick with the 4 we use. So in our labeling system, when we consider the elements, it might be convenient to maybe just write this as 1 element. This is 2 elements. This is your 3rd element. This is your 4th element. So you multiply these 2, you say, wait a second, maybe I don't have a group, this coset is not among those 4. Oh yes, it is, because it's these two cosets are equal. Even though they're expressed a different way because I've chosen to give a different representative. So let's look at why. Let's construct now the Cayley table. Again, all these calculations are done like this. You would multiply your two matrices. You get a matrix. It may not be one of the four we'll use for the representatives, but the coset determined by the matrix you get is going to be one of the four cosets. And so that's, when we fill out the Cayley table, we'll only use these four matrices. So again, this is given in the notes. And I guess I'll need to erase some more since we've got a fairly big Cayley table. So let's see if I have enough space here. So we're going to have the identity times z, that times z, that times z, and when I did my Cayley table in the notes, those are the ones I used. And then over here, we would have the same. I think the calculation, let's see. Okay, so let's multiply. This is the identity, so these will be easy. Just like any group, the first column and the first row just a repeat of the listed elements. I think actually maybe picking a different one than the, oh no, I'm okay, I've got the four I've indicated. So, what about here? This matrix times this matrix, I would get a 1 and a 1, so I get the identity. Then over here, I get a 0, negative 1, 1, 0. Well, that's not listed here, but 0, negative 1, 1, 0 is the same as that coset. And then this one would give me a 0, negative 1, negative 1, 0. Again, that's not listed among the four cosets, but it's the same as that coset. So over here we get 0, 1, negative 1, 0, which is one of our listed ones. And this would give us just 1, 0, 0, 1, give us that. And then finally this would give us negative 1, 0, 0, 1. Give us that element. And here this would give us 0, 1, 1, 0, the coset determined by that. That would give us the coset 1, 0, 0, negative 1. That's not listed, but it's equivalent to this coset. Again, what I'm doing is I'm multiplying these two matrices, and then if I have to change my representative, I'm picking a different representative for the same element and using that. Remember, the elements of this group are actual cosets, right? So it doesn't matter what we choose to write as the matrix times Z, as long as the matrix times Z for two different matrices, if that gives us the same set, that is the same element, even though it looks different. The same way 1/2 looks a little bit different than 2/4. And finally, this would give us negative 1, 0, 0, negative 1, but that's the same as the identity coset. Again, this is all included in the notes, so what do we say about this? It is abelian. But it's not cyclic. Every element is its own inverse. So again, sometimes this is called the Klein 4 group. A group of 4 elements where every element is its own inverse. And again, we can see that by this times this is the identity coset. This times this is the identity coset. This times this is the identity coset. Basically, we have the identity coset down the diagonal. That means, what's the diagonal? That's when you multiply an element by itself. So that means the square of every element is the identity. In other words, every element is its inverse. So we'll wrap up with a equivalent condition to show why something is normal. Here I'm given N a subgroup of G. N is a normal subgroup if and only if for every element in the group G, G N or G inverse N G is equal to N. So let's try to prove this. So this is an if and only if, so the way to prove this is first we have to assume N is a normal subgroup of G. Again, when we write a set less than or equal to a group, that means the set is a subgroup. When we put a triangle there, that means it's a normal subgroup. We need to show for all G and G, basically conjugation will equal this. So given an element in N, for all G and G, we have NG equals GN prime for some N prime in the normal subgroup. That's the definition of a normal subgroup. So G inverse NG is going to end up being G inverse G N prime this is just the identity, so that's N prime, which is an element of G. So what have we shown? For all G and G, since N was any element, G inverse N G is contained in G. So what I claim, this implies for all G and G, G inverse N G equals N. You may recall in the homework there was one time when we looked at a set of things, of elements in G that made this equal to N versus the set of elements in G that made this set here contained in N. But that was sort of one element at a time. It's not true for a specific element of G if this equals N, if this, for a particular element of G, if this contained and holds, we have this equality. That is not true. But what is true is if this containment holds for every element of G, then this equality must hold for every element of G. So that's what we'll go about proving. So take any x in M and any G in G. We'll certainly want to take a G inverse as an element of G, right? It's a group. So since we have this containment here for every element in the group, we have that G inverse of x times G inverse has to be in N. Again, that's this containment with G inverse playing the role of G. So G inverse, the inverse of an element of G, in particular G, the inverse of G inverse, times something in N, times that element of G, G inverse, has to be inside of N. So what that really means is that there exists a Y in N with well, let me maybe add something. We put a so. So G inverse is G. So G x G inverse is an element of N. So there exists a Y in N with G X G inverse equal to Y. What is that going to lead to? Well, we can multiply on the left by X inverse. And then the right by, multiply on the left by G inverse, on the right by G. So that's going to lead to X G inverse Y times G, which certainly is an element of G inverse and G. Since this holds for any x in N, we have that N has to be inside that conjugation. And what was special about G? Nothing. This holds for every G in G. So we've already shown this containment. Now we've got the reverse. Thus, for all G in G, G inverse N G is equal to N. So what we've shown that if a subgroup is normal, our definition of normal is the left coset is equal to the right coset. That's equivalent, that implies that for each element in the group G, G inverse and G equals N. Those two sets are equal. Let's now go to the reverse implication. Let's start from this condition and see why that will lead to a normal subgroup. And again, a lot of this work is done. We're just kind of undoing it or going backwards. So let's assume for all G and G, G inverse and G will in fact equal. Let G be any element of the group, and take any x, say, in the left coset, in the right coset, then x equals, say, n times g for some n in the subgroup. So if we multiply by G inverse on each side, we would have G inverse and G would still be in N. So by the assumption we know there exists maybe an n prime in n with G inverse NG equal to some n prime. So then if we looked at some multiplication, we should multiply, we have G times G inverse NG, so that's equal to X. So X is equal to NG, but I can multiply on the left by the identity. The identity is G times G inverse. But this is G n prime, which is an element of the left coset determined by n. So if I start with something in the right coset, the left coset determined by G. So this shows us this left coset this right coset is contained in the left coset. But what about the reverse way? To show that the left coset is contained in the right coset, what do we have? We have let's take a y that's in this left coset. So again, there exists, I think I just used a k and n with we'll say a couple things. First step is let me go to m first. There exists an m in n with y equals to g times n. But then there exists a k in n with what? With G inverse m G equal in k, or which is equal to k. Again, here's an element of m. We multiply, we've seen if we take anything in the subset n and multiply on the right by an element, on the left by the inverse of that element, that remains inside n. But as before, this is just going to be this equation here. Or gm equals k times g, multiplying on the right by g inverse, by g. And g times g inverse would be the identity. K times g would just be kg. But k is in n, so this is an element of ng. So that's exactly what we wanted, right? We start with a y in the left coset determined by g. It's got to be in the right coset. So g n is contained in ng. And that's exactly what we wanted to show. Those two inclusions together, this inclusion and this inclusion, show the two sets are equal. So together, that containment and that containment prove this equality of sets, since this holds for any G and G, we have that N is a normal subgroup. So that completes the other inequality. If you have that for all G, G inverse HG is equal to H. If that holds for every H, or for every G for some subgroup H, then that means H is in fact a normal subgroup. And let me pull out a corollary of what we showed in the proof, actually. If H is a subgroup of G, or Hn, keep switching between H and N, use N for normal. Then the following are equivalent. First is for all G and G, G inverse N, G is contained in N. The second, for all G and G, G inverse N, G is equal to N. And then the third, the subgroup is normal, which basically means for all G and G, the left coset determined by G is the right coset determined by G. And again, as I was found in the homework, it's not true if we just take a particular element, fix a G. If this holds for one G, this equality need not hold for that G. What is true is if this containment holds for every single G in the group, then this equality will also hold for every single G in the group. And we can even put a fourth thing in here, the cosets AN, where A is in G, or GN, where G is in G, form a group under G1n times G2n equals G1 times the coset determined by G multiplied by the coset determined by G2 would be, we define that product to be the coset determined by the product of G1 and G2. So those four things are equivalent. So we sort of have four different ways of looking at a normal subgroup. And I mentioned as lecture, in lecture, the face-to-face, if you're trying to show something is a normal subgroup, we like one, because it's easier to show a set is contained in a set than it is a set is equal to a set. If we know something is a normal subgroup and we're trying to prove something, we like two, because it's more powerful to know that two sets are equal rather than just one set is contained in one. So they're kind of a different, hopefully you see different advantages to looking at 1 and 2. If you want to try to show something is normal, you're a fan of 1 because that's a weaker condition, so it's easier to prove a weaker condition. If you know something is normal and you're trying to prove something else, you're a fan of 2, because this is a stronger condition, so the more things you can assume at the onset, generally the better you can do a proof. So you can take this assumption that they're equal. So we'll close here. We'll be picking up with some more examples of subgroups shortly.